Welcome everyone and thank you for joining in. I am Prima Saraya and I take care of technical marketing for semiconductors and hardware engineering at MosChip. Our session today is about unifying hardware for high speed and edge AI products. If you have ever been part of a product team waiting on a board respin, struggling with signal and power integrity closure, or wrestling with OTA updates that fail in the field, you'll recognize the pain points we are going to talk about today. Today, we'll show you how a unified approach combined with reusable blueprints can transform that frustration into predictable and first pass success. Before we dive in further, a quick note for everyone. Please feel free to type your questions in the Q&A panel as we go along. We'll take them up at the end of the session. So here's where we'll be heading today. We'll start by introducing MosChip, who we are, and why we are in this unique position to talk about this topic. Then we'll explore the problem, why fragmentation in hardware design has become the bottleneck. From there, we'll walk through the principles and methodology of unification onto how to get the first time right boards and make it ruggedized and compliant. And then we'll go to the heart of today's session, where we'll do an exclusive preview launch with all of you on our upcoming product Accelerate blueprints. This is MosChip's integrated engineering hardware to AI accelerator framework, where hardware and mechanical design, embedded software, digital sky Gen AIoT, and our newly launched agentic sky layer comes together as one cohesive stack. Together, they transform how OEMs move from functionality to connectivity, intelligence, and ultimately autonomy, not as separate efforts, but as one unified roadmap. You will see it fully in action at Embedded World North America 2025 that is coming up in next month from November 4 to 6 at Anaheim at our booth 4068. Today, we'll walk you through the blueprints across wearables, retail, automotive, industrial, and smart homes. And since this isn't just a theory, you'll hear from our practitioners who have built these systems at scale. So, along with me, we have two more speakers for the session from MosChip, Mr. Nagi Reddy, AVP Embedded Software, and Mr. Pradeep Chintala, Director of Hardware and Systems Engineering. Now, let me start with who we are. MosChip has been engineering at scale for over 25 years. We began in silicon, designing ASICs, IPs, and tape outs. Over time, we expanded into board design, system engineering, device software, and now into digital and AI engineering. Across 600 plus tape outs and 500 plus product programs, one theme that keeps repeating that we have observed is that integration gaps kills timelines. Because we operate from ASICs to AI, we see these gaps end to end. And that's why we cannot talk just about fixing them, but also about preventing them. In short, we are the practitioners who have built products for decades and we have distilled that into a unified approach. Now, let's think of a modern product as a four-layer tower. At the base, we have hardware, where silicon, PCBs, connectors, power rail, and enclosures are there. Above it, we have device software, where drivers, RTOS, bootloaders, and diagnostics happen. On top of that, we have digital layer, where there's connectivity stacks, cloud APIs, security, and telemetry. And finally, on the top, we have the AI layer, where intelligence shifts from cloud only to embedded, edge, and autonomous devices. At MosChip, we unify this stack via three initiatives. First, Gen AIoT accelerators that make devices connected, visible with OTA, and digital twins built in. Second, Agentic Sky, where the agentic AI cores that embed autonomy into devices, helping them perceive, decide, and act in the field. And the third one is the product accelerator, which are our pre validated blueprints for the first pass boards and systems. Now let's talk about the pain points. Imagine building a skyscraper where each contractor works from a different drawing sets. The plumbing doesn't line up with the electrical conduits, and the elevator shaft doesn't align with the floors. So that's what exactly is happening today in product design. PCB works in one silo. Firmware finds power instability. Compliance discovers EMI failures. And suddenly, what looked fine on paper collapses at bring up. That's why hardware unification isn't a nice to have anymore. It's the difference between delivering on time and missing the market window. And this stakes keeps on rising. A wearable today isn't just a step counter, it's a continuous health monitor. A car isn't just a vehicle, it's a software defined computer on wheels. And an industrial box isn't just a logging data, it's running AI inference in dusty, noisy factories. So, what does this mean? It needs 10 times the compute density compared to 5 years ago. It requires sub 3 millisecond latency budgets for decision making, and it needs 50 to 60% higher integration complexity if you treat each subsystem separately. So, if you don't unify hardware, you spend your cycle fixing it and not innovating it. Unification makes convergence manageable, and that's why convergence isn't optional anymore. It's the only way to make products faster, smarter, and still predictable. So, with this, I would like to hand over the session to my colleague Pradeep to take it further. Over to you, Pradeep.
Thank you, Prima, for providing the insights into how hardware unification has become part of design process and not being an optional one. I am Pradeep Kumar Chintala, head of the hardware board design group, having over 2 decades of multi-domain industry experience. My primary responsibilities is architecting comprehensive platform solutions and pre-silicon FPGA boards to post-silicon evolution boards. My team's expertise spans the full spectrum of complexity, from two-layered boards to the complex 22 to 40-layered high-density PCBs with thousands of components on them. We specialize in utilizing a wide range of dielectric laminates to meet stringent interface requirements for extremely high speed and low latency and low loss performance towards successful and reliable products, which are field deployable, agile solutions for customers to use these across industries like smart factories, autonomous or self driven vehicles, industrial IoT, smart healthcare, drones, and security and surveillance. With this, let's now talk about typical hurdles that can derail the complex hardware designs. As we go through these hurdles, I will share how our team at MosChip leverages its extensive experience to provide clients with a clear path to a solution. As every hardware engineer knows too well, the board comes back from PCB and PCB fab and it just don't behave. You power it on, and instead of satisfying movement where SOC boots cleanly, you are chasing the ghost. For example, memory fails in calibration, PCI Express lanes dropping packets, the PDN sagging, thermal choking every time the AI accelerator kicks in. Why? Because an edge AI design, you're packing DDR running at giga transfer per second, PCI Express Gen 5 highways, MIPI related camera and display lanes, and 15 watts of SOCs all into the same cramped stack-up. Without unification, each team optimizes in isolation. SI ranks in one corner, thermal in another, power in another, and when all comes together, the eye diagram is closed, the PDN collapses under load, and your pilot board is suddenly a 6 months respin. With unified design, these trade-offs are balanced upfront. The eye diagram is stimulated before the PCB fab. PDN stability is tied to thermal headroom. Firmware hooks are aligned so you can test real workloads on day one. Unified thermal solutions prevent performance throttling in dense edge AI hardware through advanced materials and integrated cooling strategies. So instead of chasing ghosts at bring up, you are watching the board boot cleanly on first pass. That's the difference unification makes. Today, I am excited to share that this is the first time ever we are revealing MosChip's consistent and proven design methodology to the global audience. We are concentrated this into a framework we call MosChip. Think of it as a four guardrails that run together from the initial architecture, schematic, PCB design, mechanical design, and onto the final product realization. Manufacturing optimization, engineers don't design a beautiful board that can't be built at scale. By following manufacturing optimization strategies like design for fabrication, design for assembly, design for testability, design for manufacturability, design for cost, with mechanical integration, with meticulous cable harnessing, and ensuring optimal cost and competent products. Signal integrity challenge, making sure the waveforms in your head actually stay cool when they hit copper on the PCB. Comprehensive analysis and mitigation for EMI, insertion and latent loss, and crosstalk elimination with proper maintenance of characteristic impedance at board level. High speed logic is considered as the subtle stuff. By factoring high speed and high density interconnect implementations with critical length matching, timing margins, glitch free DDR calibration, the eye diagram analysis, and the SOC to RAM interface optimization can be achieved. As part of power and thermal integrity, a stable power rail on the bench means nothing if it sags under an AI workload. Advanced decoupling, thermal management solutions, voltage rail optimization, and ground bounce elimination strategies to be applied early in the design phase. When all the four guardrails are in place, you don't end up with firefighting in validation. You end up with a board that comes back as from an assembled platform, boots on the first try, and passes compliance without any drama. This is the difference between firefighting late and engineering confidence upfront. Let's discuss how MosChip deals with domain-specific issues and kind of checklist we follow. Every vertical has its traps. We shall now quickly discuss few of the domain-specific pitfalls. Automotive gateways fail EMIMC if PDN noise is in control. Industrial gateways suffer connector and component failures under thermal stress over a period of time. Wearable gadgets run out of battery because burst overload or workloads weren't profiled well. Moreover, testability is a must-have feature in any design which shall enable engineers to carry out RMA and FA of the units from field. Identifying these issues and following critical checklists are part of how we bake collective memory into every blueprint. So no one has to relearn painful lessons. Till now, we discussed MosChip methodology and the potential pitfalls during any platform design. Now, I shall showcase few example simulations which must be carried out at the PCB level to avoid respins. For example, selection of proper dielectric laminate, freeze the stack up of the PCB in line to the PCB fab house design capabilities, high density interconnect PCB, which utilizes micro wires with laser drilled holes with diameters as small as 50 to 150 micrometer. Blind and buried wires, wherein holes that don't go all the way to the board, but it goes to the specific layer in the dense boards. Next, we shall go through the signal integrity simulations, which consist of a minimal coverage of insertion loss, return loss, near end cross and far end crosstalks for the parallel bus like DDR4, DDR5, PC Express Gen 5 SerDes lines, and I diagrams to be clean for reliable signal quality, and lastly, the time domain reflectometry for any reflections at the signal level. And this will make sure to pass the product in complex real world environments. Moreover, power integrity needs utmost care, which includes the DC drop analysis, and it is also called the IR drop analysis of the power rails, decoupling capacitor analysis, and wire modeling in concurrence with the rail-wise wattage specification defined for that particular product. These simulations ensure that the PCB and the subsequently the end product remains reliable, fail-safe, and free from performance degradation over time. Our portfolio demonstrates expertise across diverse form factors and applications from high-density industrial systems to specialized storage platforms and IoT gateways. On the left side, you see the IPC motherboard, which is designed for a customer to enable them for the field deployment with design for cost taken into consideration. In the center image, you see the high storage memory application like potted black box used in the navy ships or aircraft sort of applications wherein the memory density ranges from terabytes to petabytes. And this black box will be mounted on the tray-like complex PCB with HDI concept being followed, or which runs on the PC Express backplane, and it is targeted for 3U and 5U server mechanical chassis, and which was enabled to a cloud store and access for that memory density. On the right side, you see a home automation IoT gateway being deployed in homes to automate the wireless home appliance nodes. Multiple wireless profiles are being arranged and tested successfully in the custom built ABS enclosures. Before I start the topic of initiating ruggedization for products intended to get exposed to the harsh environments, I want to emphasize that the testing requirements will be significantly more stringent compared to those of the industrial and edge AI applications. Ruggedization term emphasizes real world conditions which are unpredictable and often more extreme than controlled laboratory testing environments. As we all know, products don't live in labs. They are in cars on highways, boxes in factories, variables in rain, modules in airborne. For product developers, this means designing and testing must go beyond the lab to ensure reliability, durability, and safety in actual use cases. We design for vibration, dust, heat, and unstable power environments. That means unified thermal paths, hardened power stages, EMIMC compliance baked in, wherein ruggedization isn't an afterthought, it's a design principle we follow. Our product ruggedization strategy is all inclusive. That means EMI/MC and ESD compliance, considering shielding, filtering, layout discipline aligned to the certification standards, and thermal resilience by following conduction cooled housings, wire forms under BGS, derating models for ambient extremes, power stability by following transient protection, surge handling, graceful degradation under brownouts, mechanical integrity by following proper selection, proper selection of materials, mountings, and the connectors designed for shock, vibration, and ingress protection. And more importantly, maintainability. The field replaceable module, built-in telemetry, and diagnostics that keep service engineers stable. As you all know, engineers often spend months addressing complex EMI/EMC compliance challenges for products, which include conduction emission and susceptibility, radiated emission and susceptibility, as well as HBM and CDM ESD evaluations. Design is only half the journey. The other half proof it survives reality. We carry out CISPR 11 and 32 Class A, Class B emissions and humidity checks for all the ISC and ITE products we design. For defense and aerospace, we run more stringent safety of flight tests, MIL standard 810G and 461E compliance checks to make sure they are pushed across the domain. So we push our systems through thermal cycling, humidity chambers, vibration rigs, high altitude, acceleration, damp test, salt corrosion, mold test, and shock test post the conformal coating measures at product level to make sure the end product is more rugged. It's about building confidence that once deployed, the product doesn't die in the wild. Certification becomes the stamp on engineering discipline. Here are some real world examples MosChip design passing the stringent ESS safety of flight test. A servo storage unit with consideration of thermodynamic and noise controlled chassis design. Couple of avionics SBC qualified DO254, SOFT and MIL standard specs. Rigid flex variables are tested to survive curvature builds, motion and drop cycles. Additionally, thermal analysis is not only at PCB level, it's at most important to carry out at the enclosure or the chassis level, considering the harsh dynamic environments as part of ruggedization. Different markets, but they shared one single story. Ruggedization wasn't patched on, it was designed in. All of this sets the stage for unification, not just in design, but in deployment. And that leads us to modularity. One of the most powerful accelerators we use is modularity. With smarts or custom SOM, compute becomes a drop-in block. You don't redesign DDR, PMIC, or flash or boot every time. You focus on your carrier board and your unique IOs, isolation and thermal. This means faster prototyping, predictable thermal, easier compliance, and serviceability. Think of it as a reusing a trusted engine block while customizing the rest of the vehicle. Here you can see MosChip customized design Smart 2.1 enabled platform which is compatible with a wide range of vendor specific standard smart modules, for example Renesas and Qualcomm. Here you can see that this is one of the example which is Smart 2.1 enabled platform wherein Renesas sort of SOM is been mounted on the board. Next is the small form factor Jetson Nano carrier board, which is compatible to multiple variants of the Jetson Nano with expansion scope to enable customers for simple replaceability across applications and use cases. And here I would like to showcase this carrier board with Jetset Orient card mounted as a SOM at this custom built in-house to the MosChip. Okay, next we want to showcase the SOM, the MosChip SOM. Yeah, this is MosChip's SOM, which is AMD Zinc UltraScale Plus module, which is the form factor of the credit card. And this modularity approach will make the customer use as a simple drop-in use case with a simple carrier board designed by the customer and easily end towards a solution with carrier plus SOM towards any edge AI applications running on it. All of this boils down to three simple anchors: standardized compute and interconnects, use known good SOMs, validated high-speed interconnects, and wireless interconnects, validated SI and PI and thermal templates, pre-engineered PDNs and thermal envelope, so your envelopes are so you are not reinventing power every time. Common firmware and OTA baseline. secure boot, telemetry, and update pipelines baked into every blueprint. Three anchors that remove guesswork and replace it with reusable confidence. Hope you had a good understanding on how hardware unification and constraint driven ruggedized products are designed. Now I hand over to Mr. Nagiredi to take you through some of the recent product accelerate blueprints. Thank you.
Thank you, Prima and Pradeep, for providing insights about MosChip and sharing some of our complex hardware design learnings over the past 2 decades. So, myself, Nagiredi, AVP in Product Engineering BU, I have over 2 decades of experience in designing and developing firmware, bootloaders, and system software components for multiple domains. My primary responsibility is architecting and handling firmware components, BSPs, and pre and post silicon validation related projects. My team expertise spans across full spectrum of firmware, BSPs, various operating systems like Linux, Android, and RTOS, and device drivers. So let me walk you through some of our recent product accelerator blueprints we have developed for various vertical segments. As I walk you through them, we'll share how these product blueprints can help customers to cut down their execution cycles, development costs, and time to market. So all these key advantages are coming with the help of hardware unification. As Prima mentioned about our product accelerate blueprints, it converges hardware and mechanical designs, embedded software, digital sky, Gen IoT, and our newly launched agentic sky layer coming together as one cohesive stack. So it makes unification real and repeatable. It is not just a reference design, not a kit, but a strategic foundation that helps your product climb the ladder from function to connectivity to personalization and to adaptiveness and finally autonomy. So how does it do that? By embedding the building blocks below. The hardware plus mechanical. MosChip's pre-validated chipset or SOM SoC from wide variety of choices can help customers to choose the right combo for their solution and avoid spending months of time in feasibility study for the right platform. Next, embedded software. Pre-validated libraries and stacks for various protocols can help to get the functional prototype quick. MosChip's Gen IoT module that gives your products universal connectivity, security, OTA capability, and observability from the field. MosChip's Agentic Sky cores that add perception, interpretation, and decision making. So your devices don't just respond, they anticipate and adapt. And the underlying unified hardware blueprints that guarantee high-speed performance and ruggedization and compliance out of the box. So when you adopt a product accelerate blueprint, you are not just reducing time to market, you are stepping onto a roadmap from the AI-led product era, a roadmap where each product you launch can evolve from connected to intelligent to autonomous. That means instead of waiting a year for prototypes, you have pilots coming up faster, cut the development cycle time by 40%. Instead of reinventing each SKU, you can reuse up to 40 to 60% components. And instead of switching complaints late, you are certification ready from day one. So product accelerate blueprint is how you stop treating hardware as isolated projects and start treating it as a continuum of innovation. So let me walk you through one of the important blueprint which we designed at MosChip for variable segment. The variable companion blueprint demonstrates how a unified hardware and AI stack can accelerate the development of compact, intelligent variables. It's built around a rigid flex board combining a 1.2-inch AMOLED display on the NXP's AMX8M mini SoC with an Android 15 build optimized for variable fusion. This design has a few more components like PCA 9450 PMIC, dual band antenna with diversity, 5MP autofocus camera, USB SDM pads, audio interfaces, and Murata Wi-Fi plus Bluetooth combo. Design has eMMC 5.1 HS400 and LPDDR4X memory. providing a stable high-speed performance for multimedia and sensor workloads. The rigid flex sensor card integrates pulse oximetry and heart rate monitoring sensors, an environmental sensor and ambient light sensor paired with the 1.2-inch square display option, and a 6-axis IME for activity tracking. This architecture delivers a proven hardware foundation for wellness and preventive care devices that require precise sensing, low power operations, and reliable OTA management. On this hardware, Gen IoT provides a digital layer for IoT onboarding plus OTA, cognitive models, unified automation for QA and power regression boards, dashboards for user and enterprise analytics. Agentic Sky builds the intelligence layer through variable core, enabling sensor fusion, autonomous behavior, and proactive nudges that personalize the user experience while maintaining transparency and control. Together, these layers move the product from a basic connected tracker to a self-learning health companion, one accelerator supporting multiple profiles, including regular lifestyle, healthy living, patient monitoring, and elderly care, all without changing the core electronics. And let me walk you through another blueprint which we designed at MosChip for segment, retail gear segment. This accelerator is built around a Qualcomm's QCS 8250 SoC, an Android 15 profile, and ruggedized gears design engineered for high-speed vision and HMI applications. It supports the full retail transaction flow, scan to card to pay to receipt, and is optimized for 24/7 operation in public environments. The hardware integrates PCI Gen 3, multiple USB 3.1 ports, and high bandwidth camera, and with a couple of display interfaces. With three 4-lane MIPI CSI camera ports, a Spectra 480 ISP, and a 64 megapixel camera interface, 34 frames per second ZSL support. It can run multiple concurrent vision streams for barcode, face, and object recognition. The display subsystem drives up to three 4K displays through DSI and DisplayPort 1.4 with the touch control. So backed by 8 GB LPDDR5 memory and a 125 GB UFS storage. On this foundation, Gen IoT handles IoT and connectivity services like OTA updates, providing cognitive intelligence for 20 plus version and speech AI models, and supporting unified automation with the DevOps and test boards. It also powers digital or native dashboards that track checkout KPIs, detect fraud attempts, and measure dwell time or ad view analytics. So Agentic Sky adds Vision Core and HMI Core components. Vision Core mainly focuses the fuses face, fingerprint, and liveness data with the spoofing detection. HMI Core governs the explainable user interactions during payment, ensuring transparent and guided transactions. Together, these layers deliver an autonomous, transparent, and trusted checkout system, a kiosk that can adapt to challenging retail patterns, run secure in-store analytics, and integrate seamlessly into connected retail networks. This should turns every kiosk into a small node in your retail network. So we can think of a couple of broader applications with the same blueprint, mainly towards a smart kiosk, self-checkout in supermarkets, malls, airports, and digital assistant in auto showrooms, smart receptions, desks in offices or hotels, a banking kiosk for self-service like account opening and KYC related tasks. Now, let's dive into what MosChip is offering for automotive space, and that's the SDV blueprint. This SDV blueprint accelerator built using NXP32G SWARM with the AWS SDV integration. It's engineered as a SOFI CodeSaver compliant gateway that manages data between vehicle domains, ECUs, and the cloud systems. This gateway supports up to 8 Cortex A53 clusters, dual or quad-core lockstep M7 controllers, and a 16 source isolation domains, providing a secure deterministic base for mixed criticality workloads. Networking includes 20 CAN FDs and FlexRay and 3 2.5 gigabits Ethernet interfaces, while hardware acceleration is handled by the low latency communication engine and packet forwarding engine. With LPDDR4 and eMMC memory, AMC storage, it's built for continuous operation across automotive temperature ranges. Gen IoT manages IoT and connectivity, mainly CAN ingestion and VSS mapping, and the cognitive modules, unified automation, OD orchestration, regression automation, etc., and digital dashboards for fleet lifecycle and proactive insights. So Agentic Sky introduces the controller core, which applies self-healing logic, diagnostic modes, and optimization guidance to ensure safe adaptive gateway operations. The result is a future-ready SDA backbone, a gateway that connects current ECUs and sensors while scaling towards autonomy, a secure data exchange, and real-time fleet intelligence. So there are a couple of possible other products and solutions we can think of with this blueprint. Software-defined vehicles for passenger cars, fleet management and proactive maintenance, are R&D demo for Tier 1 OEMs, OEM labs. So here I would like to show you the ruggedized board. This is a front view, which I have used for this solution. And this is the heart in the whole design. And this is the back rear view. It's such a complex board. It's a 10 layers board. Now, this is the board I was showing you. We have spoken about wearable and retail and automotive related blueprint accelerators. However, MosChip has built two more blueprints for industrial and homes. Let me walk you through these accelerators. So the industrial BMS gateway blueprint built with a ruggedized IMX 18 plus board with validated interfaces like Modbus, OPC, UA, backnet, all such protected and uptime tested interfaces. This rugged accelerator is built on the industrial grade NXP IMX 18 plus core SoC with Linux or Acto stack with backnet or Modbus interfaces. It targets factory, building, and energy systems where repeatability, uptime, and predictive automation are essential. The core architecture combines a quad ARMS Quad A53 CPU, a Cortex M7 controller, and a 2.3 TOPS NPU. Complemented by the Tensilica Hi-Fi V4 DSP for low power voice and audio tasks. The board integrates multiple PCI Gen 3 buses and USB 3.0 gigabit Ethernet ports with one TSN support as well as a complete IO set like UART, SPI to see all low-speed buses and the peripherals. It supports up to 8 GB LPDDR, 64 MB NOR flash, and dual ISPs for up to 12 megapixel input processing. Gen IoT manages OPC, IO link, and MQTT connectivity, along with multi-protocol device onboarding. It provides cognitive models that monitor occupancy, vibration, humidity, and energy consumption, feeding dashboards that report OE, carbon footprint, and predictive maintenance alerts. Agentic Sky extends this with the controller core, implementing self-healing policies, degradation modes, and optimization logic that sustain system performance even under partial faults. This accelerator forms the basis for industrial and building management systems that can self-monitor, self-correct, and operate continuously across rugged, high availability environments. So there are various other solutions possible with this industrial gateway blueprint accelerator, mainly factory floor monitoring, predictive maintenance, smart logistic hubs like conveyor belts health monitoring, and the building energy management, power plant automation, etc. And the mining industry, also mining heavy machinery health monitoring. So here I would like to show the board we have used. We have designed the ruggedized board. This is the front view of the board and the rear view of the board. And this is a 12-layer board. Now let me walk you through a home hub blueprint. This blueprint accelerator uses Infineon PSoC as a matter-ready hub for secure, interoperable smart home devices. It features a dual Cortex M4 plus M0 combo architecture with CapSense inputs, extensive serial interfaces, and a Murata Wi-Fi plus Bluetooth combo. Power management supports 1.8 to 3.3 volts operation, and a memory includes 2 MB flash, 1 MB SRAM, and external SPI NOR flash FRAM combo. The design supports full-speed USB, micro SD, and dual-band Wi-Fi or BLE connectivity, making it suitable for hubs, bridges, and controllers that integrate Matter, Thread, Zigbee, and Z-Wave ecosystems. Gen AIoT provides secure lifecycle management, onboarding, OTA updates, and monitoring. It also hosts adaptive user behavior models, regression boards, and unified dashboards for energy usage and anomaly tracking. So Agentic Sky contributes the controller core, enabling mesh network rerouting, fault recovery, and adaptive automation logic. This allows the hub to maintain service continuity even if a node fails, ensuring that home environments remain predictable and autonomous. The accelerator supports multiple household scenes like wake up, wind down, night, energy saving, or focus modes, where devices automatically adjust lighting, temperature, and power usage based on learned patterns. It represents a trusted reference design for secure, adaptive home automation. So there are a couple of various other solutions possible with this blueprint on the home automation segment. The smart home hubs or bridges, energy saving automation suites, smart lighting scene controllers, the safety security systems, appliance environmental control units. So let me show you the board, a carrier board, which I have designed with a PSOC, Pinion PSOC architect. This is a front view of the board, and this small form factor, the rear view of the board. So with this, this was all about product accelerate blueprints we have at MosChip. Let me now hand it over to Prima to take forward.
Thank you, Nagi, for sharing the insightful preview of our product accelerate blueprints. So that's the story from us. We started with the problem, fragmentation, and respins. We saw the principles, MosChip, and ruggedization strategies. We explored how unification works across high speed industrial, automotive, and consumer systems. And we landed on product accelerate blueprints, a roadmap to the future of products. So, from functionality to connectivity, from connectivity to personalization, and from personalization to adaptiveness, and ultimately to autonomy. So, if you are building the next generation of connected, intelligent products, the blueprints can accelerate your journey from idea to reality. At MosChip, what sets us apart as your partner in this journey is the combination of proven design experience that we have, a complete concept to manufacturing ecosystem, and strategic industrial partnerships that gives us early access and adoption opportunities to new technologies. With this, we will now open the floor to take up the questions, and I once again thank you all for joining today's session. So, we have a question. So, it says, can unified hardware reduce dependency on specific vendors or mitigate supply chain disruption? I think, yes, would you
Yeah,
like to take it?
I'll take it up. Yeah. So yes, with unified hardware design and the designing products complying to smart and other alternatives like Q7, COM Express, COM HPC, and Vita and VPX sort of standards, and an open and vendor independent form factor for computer on modules, which are part of embedded system components, addresses the supplier diversity, interchangeability, processor agnostic design, increased competition as second source. So with the hardware unified thing, and not stick to some specific proprietary thing, instead of following the standard smart form factor and connector definitions, well, its answer is yes, we can do that.
I think we have one more question. So that says, what steps are critical during hardware validation to ensure compliance across automotive and defense grade products? I think, yeah,
Okay,
Pradeep, you can take that.
sure. So as the question goes, I will split the answer into two. One is the automotive domain, and another is defense and military. So coming to automotive, AECQ component qualification, the cornerstone of automotive hardware reliability is ensuring that every component on the board meets the Automotive Electronics Council, like AEC standard. Validation should involve subjecting the components and also the complete system for the rigorous test, including temperature cycling, high temperature storage, and humidity test to prove their robustness. And also, one should make sure we follow ISO standards, for example, 26262, as part of functional safety analysis, comprising of failure analysis and diagnostic analysis, fault injection, and EMC compliances. Secondly, when it matters to the defense, for the PCBs falling under the mill grade, so we need to follow mill PRF Group A and Group B constraints for the PCBs. And for the end application of the products, we have to comply for mill standard 810G and 810H. And for the power and the vehicles perspective, we have to make sure we follow mill standard 1275, wherein the temperatures can range from -55 to 125, and it's harsh environments. And as part of the EMAMC, we should make sure the product complies and be thoroughly tested to pass the 461G, wherein, as I earlier mentioned, so we have to go with CE, CS, RE, RS, and stringent CS 118 ESD testings to make sure the product is well, and it's ruggedized, and it is harsh environment worthy. Yes.
Thanks, Pradeep. I hope that answers the question that came from. Okay, so I think we can wrap up our session here. So, once again, thank you all for joining in. And if you have any questions on this webinar, or you would like to connect with our team, please feel free to reach out to us. And we'll also be sending a recording of this session to all of you. So we definitely look forward to receiving your queries over email. Thank you once again for joining in.
Thank you.
Thank you, audience. Yep.
Yeah.